Anyway, so the title is Primordial Black Hole and non-Gaussianity. This is based on my previous work for the past few years. Because not all of us are experts in this field, so I will try to make it more easier to the people from all the fields. So anyway, so this is the content that will introduce what is a primordial black hole and why it is important in the recent years, and primordial black hole formation and the observational constraints. Then I go to the third part, which is mainly contributed by myself and my colleagues, about the non-Gaussianity generated during inflation and their impact on the previous formation. If I have time, I will go to the recent topics on the prediction in the millihertz and the nanohertz gravitational wave observation and predictions. So yeah, this is what I call. When I transfer the slides from Keynote to PDF, it jumps all of a sudden. So it's not. But anyway, so let me start from this part. We have the CMB anisotropy. This is the I think this is the most important cosmological observation in the past 50 or years. It kind of identified that this cosmic perturbation from this density fluctuation, large scale structure, whatever, comes from the quantum fluctuations during inflation. So by doing so, you can reconstruct from the CMB anisotropy on all the scales. This angular can be transferred to different scales. The power spectrum of the curvature perturbation on super-Horizon scales. And this is the initial condition for the CMB anisotropy and large scale structure. We know that the power spectrum of the curvature perturbation on Communion slice, which I wrote this curly R, is of order 10 to minus 9. And at the same time, it's nearly Gaussian and adiabatic. So this is the so-called one of the most important ingredient of the lambda CDM model, which predicts all of the universe we will observe today. But this is only on large scales. Roughly speaking, is scales larger than 1 megaparsec. So if you go to smaller and smaller scales, you are losing your resolution of the observation. You can see it from here. So this becomes huge because this is the 1 sigma, 2 sigma uncertainty, which means that you cannot say anything by the Planck or whatever. So this means that you may have possible enhancement of the curvature perturbation on smaller scales. And also you should doubt whether it is still Gaussian or adiabatic on a specific scale, which is much, much smaller than this megaparsec, maybe kpc or parsec or even smaller. So what will happen is,
in the graph of CMB anisotropy, does it mean that if it is smaller and the smaller scale or higher L, then the anisotropy is becoming smaller and smaller?
Oh, you mean this part?
Because it is getting down.
Oh yeah. This is because if I re-enter the horizon, then it started to oscillate and decay. Because the equation of motion is tells you that when you re-enter the horizon, then because of Hubble friction, the amplitude is going to going down. So this is the famous so-called sig damping.
They came into the horizon much earlier, so they damped quite much.
Yeah. So if you look at these large scale ones, they are not decaying at all. So they almost preserve the primordial value, and the reconstruction is mainly by this part. So you can have a nearly scale invariant power spectrum on super horizon scales. Of course, if it re-entered the horizon, then it started to decay. That's what we learned from this modern cosmology.
So if they were exactly flat, it's supposed to be flat in the middle term.
If it's if it can
invariant in the case of Hamilton's damage. So
if you can extrapolate this nearly flat power spectrum, all the scales down to the very small scale, then nothing will happen, of course. Yeah. So we assume that there is a enhancement on small scales, which can give you such interesting phenomenology because we have observational implications of that, which I will come back later. So anyway, so this enhancement of the curvature propagation on smaller scales, like for instance, enhanced to 10 to minus 2, can have two interesting phenomena. So one is through this nonlinear propagation, because this is a curvature propagation, and you have we know that in the propagation theory, this scalar, vector, tensor type are separated. They do not couple to each other at linear level. But at non-linear level, they can couple. So two of these curvature propagation can induce one of the tensor propagation. This is called the induced gravitational wave. It's studied a long time ago. And the other side is that because this curvature propagation is already very large, and this is actually the variance of the curvature propagation. So variance is 10 to minus 2, then there are some extreme values which extends to like order 1. And that part, rare part of the universe will go through this gravitational collapse and get rid of this Hubble flow, and then finally it collapses into a black hole. This moment is far before the recombination, so it's called a primordial black hole. And this one is not collapsed because of the baryon matter, so it's one kind of a dark matter. And this kind of dark matter can be all the dark matter we observed today, based on the observation.
So you said nonlinear perturbation. You said there were two perturbations that is independent at the linear level.
Yeah.
What are those two? One is the scalar curvature.
Scalar curvature propagation, scalar typed curvature propagation, vector typed propagation, and tensor typed propagation. These three parts are decomposed. This is called decomposition theorem in the cosmological propagation theory. Decomposed means that if you look at the action at the quadratic order, then you can only see the quadratic order action of curvature propagation, like r squared, or v squared, or t squared. There is no terms like RT, RV, whatever. It doesn't exist because of these constraints or whatever. But if you go to higher order, on the third order, you have this RTT, RVV, something. And such kind of a RRT term will induce the nonlinear propagation, which means that if you write down the equation of motion, then the source term will be a quadratic source of the curvature propagation. I will come back to this later. Yeah. So this is a metaphor of what is happening actually. So this C is like our early universe. And you can see that there are fluctuations. These waves are like the fluctuations. That's the density fluctuations and so on and so forth. But you have to satisfy some condition. For instance, this wave is high enough that it reflects the sunlight to the observer, and you can see this a light spot. And this can be seen as the primordial black hole. It's a rare event, but the condition to form it is the wavy structure of such an ocean. But at the same time, such an ocean is moving around, and this is the so-called stochastic gravitational wave. So you can see this more clearly in this is also schematic from Williams' paper. In this paper, he showed these two pictures are identical. So it's some kind of a space. You have a density fluctuation, which is shown in this color. So you have a overdensity and underdensity. And you can see that there's a characteristic scale of this. This is supposed to be the Hubble horizon. So around this Hubble horizon, if this one is high enough, if this the peak of the density fluctuation is high enough, you can see that it's like order 1, then it can collapse into primordial black hole. In this picture, you only have this one primordial black hole. The others are not high enough. And the characteristic scale is exactly the horizon scale at the fluctuation, the re-entry of the curvature propagation, and which is at the same time can be depicted by the wave number of the peak for the power spectrum. At the same time, you can see one of the gradients for the density fluctuation sources induce the gravitational wave. So you can see such kind of quadruples everywhere, and this one including this primordial black hole. So these sources can give you this continuous and stochastic gravitational wave background you observe later, which means that at the current level.
So the density plot and also I think that's for the curvature curvature scalar fluctuation.
That's true. I think he's drawing a density fluctuation here. This delta is delta rho over rho. Delta is delta rho over rho. But this can be connected to the curvature provision by the Poisson equation. Nabla squared r is delta. So it's basically the same if this is sharp enough. I come to this immediately. So if you want to look at this picture more precisely, then let's go to the space-time figure of our universe. This axis is the scale factor A in logarithmic scale, and this is the physical length of L, also in a logarithmic scale. And this colored thick curve is the Hubble horizon. So during inflation, we have a Hubble kind of a scale, which is a constant. And after that, it started to grow proportional to A squared in the radiation-dominated universe, and started to grow proportional to A to 3/2 in the matter domains, and then dark energy and so on. So the largest scale we can observe is somewhere here. This is this so-called 10 gigaparsec or something. But this is highly constrained by CMB and molecular structure. We are talking about some smaller scale depicted here by this K star. So it starts to grow proportional to A, so A over K star, and supposed to be large. And after you re-enter the horizon, this scale collapses into primordial black hole and at the same time induce gravitational wave. The connection of this is depicted by the Einstein equation. So G mu nu equal to T mu nu. I just get rid of all the indices. And the 0, 0 component is the Poisson equation. So Nabla squared of the curvature provision is the kind of density fluctuation delta. And the Ij component is the equation of motion for the tensor fluctuation Hij. So this is usually 0 on the right-hand side. If you only stick to the linear level, so it's a box Hij equal to 0. Then you have this, you can solve this equation of motion for Hij, and you find that it's proportional 1 over A, and that's the primordial gravitational wave we observed today. But now, if we go to one higher order, then you can have the source term of all of the quadratic terms. And the largest one is the quadratic form of the curvature provision, Nabla IR, Nabla J. So this kind of a gradient of the curvature provision will serve as a source for the gravitational wave, and this is called the induced gravitational wave. So in this case, let's say if this curvature provision has a Gaussian distribution like this, and kind of a primordial black hole formation will happen at the tail once it reaches some large value. This is called a critical value of the density fluctuation. So, and if you cut here and integrate, then you have a complementary error function. So this is a kind of a textbook calculation. And this one depends on the critical value, which is determined by the numerical simulation, and also the variance of the PDF. So this is also easy to understand, because if you have larger power spectrum, variance of the power spectrum, then this PDF becomes fatter. It becomes fatter than this part. The tail part is larger, you have more primordial black hole. On the other hand, if this is smaller, then primordial black hole abundance is also smaller. So remember that this sigma delta, the variance of the density fluctuation, also re-enters in the source of the gravitational wave. Because this is of the same order of the curvature provision, because of this is a linear relation. So if you solve this equation of motion by the Green function method or whatever, then you can calculate the spectrum, energy spectrum of gravitational wave, omega GW. is a redshift factor of 10 to the minus 6 times the power spectrum of curvature probability squared. So if you write it in the sigma delta, then it's a sigma delta to the fourth, something like that. So this one, as well as this one, they are the same thing. So by this means, I say that you can cross-check these two. This cross-check can be used to compare with the observations. Let's say, so if we have, for instance, this is the observation of primordial black hole abundance.
So in the previous one, you mentioned the original the gravitational wave and the induced one.
Yeah.
So when you say the omega gravitational wave, that's the both. So everything is, well, let's say induced gravitational wave is always suppressed very much compared to the primordial.
Primordial gravitational wave is always suppressed. Yeah, it's also some redshift factor times this amplitude is Hubble, right? So it's suppressed by this factor. This is usually like 10 to the minus 10 or even smaller. So it's roughly speaking is 10 to the minus 16. Let's see. So this is always smaller than this induced gravitational wave if the power spectrum of the curvature propagation is enhanced to like 10 to the minus 2, something like that. So you can see that if this is let's say power spectrum 10 to the minus 2, then this is 10 to the minus 10. So 6 orders higher than this. So you can in this method you can just estimate, and you can see that unless the curvature propagation is enhanced, this induced gravitational wave cannot exceed this primordial one. Yeah. Anyway, so this is the way we do this cross-check. Let's say this is the figure. It's the percentage of the primordial black hole as all the dark matter. So this is like a primordial black hole to be all dark matter, 10% of dark matter, 1% of dark matter, and so on and so forth, with the constraints. Which is why I will come back to the meaning of all these constraint lines later. It is possible that the primordial black hole can be all the dark matter, which I showed here as a PBH equal dark matter. So if this is true, then from this, you use the method I talked about before. You can calculate or reconstruct the power spectrum of the curvature propagation. And we see that, okay, it's 10 to the minus 2. And then we use the equation of motion for the tensor fluctuation and solve it, then evolve it to the day. You can calculate the omega GW. As I said, it's 10 to the minus 6.5 times the power spectrum squared. And you can see that it's 10 to the minus 9. So this is kind of a rough estimate, but the number is correct. So if primordial black hole are all the dark matter, the induced gravitational wave will be like 10 to the minus 9, 10 to the minus 10, around here. Interestingly,
so the correlation between the density of black holes and of gravitational waves depends on which parameters. I mean, it's fixed. For instance, you assume that all the black holes have the same mass, or
yeah. This is what I assume. So a so-called narrow spectrum of the curvature propagation. Yeah, this is something that you pulled by hand due to the observational constraints, for instance. Like for instance, if you look at this figure, you cannot put primordial black hole to be all dark matter in either here or here because they are all excluded by the observations.
Yeah,
this
but
is
you have different fractions of different mass.
Yeah, that's true. That's true. It can be a broad power spectrum. Yes, that's true. That's what some kind of advanced topic. I may come back later, but yeah.
In the case that you have only one mass, this correlation is fixed. So what are the free parameters then? So you just reconstruct.
Yeah, in this case, no free parameters. Everything is fixed.
So in other words, if you have the correct Rayleigh abundance, you have this prediction is irreducible.
Yes.
And you cannot get rid of it.
Yes. This is a kind of a robust prediction. And actually, we made that in like 2018. That is actually, we claim that if primordial black hole are all the dark matter, you must see this signal in the space-bar interferometers. These are Taiji, Tianjin, whatever. That's
Here, so the reason why you chose primordial black hole mass, for example, as a 10 to minus 15 of the
Solar mass.
mass,
Yeah.
is because that is the only region allowed from the observation, right?
Yeah, that's true.
Colored region means they are excluded.
Yeah, by other observations. This is microlensing and so-called electrogalactic gamma rays.
This thing is just nothing but the middle value of the open window.
Yeah. You can change. You can move around. It doesn't matter. You move around this, then you move around the peak of the induced quantum wave signal. So it also moves around.
Yeah.
But you can show that no matter, as long as this peak is inside this mass window, these gravitational wave signal are always detectable by the interferometers. I forgot to put this figure, but that was shown in our very recent paper written for the Tianjin white paper on scientific goals. But if you're interested, I can send you later. Sorry for that.
So the K star corresponds to the size of that the primordial black hole.
Yeah, that's true. If you look at this Williams good picture, the K star is this KP, so it corresponds to the comoving size of the horizon, Hubble horizon. But of course we are always calculating in real universe. So times 8, then you have the physical length. So this is determined by the size. So let's say so this K star determines the mass of the primordial black hole, and also it determines the frequency, the peak frequency of the induced gravitational wave. And the reason is very simple, because as I said, or is shown by the Williams figure, that 1 over K star is the horizon size at the horizon reentry for this fluctuation. And this horizon size can determine the primordial black hole mass, because primordial black hole mass is approximately the horizon mass when it started to collapse. That is more or less 1 or 2 times of this horizon mass, but it's basically the same order. And at the same time, this is the characteristic wavelength of the fluctuation. So the frequency is also determined by this horizon size. So this K star determines both of these two. So once you know this, then these two are fixed. If you, actually, this is not an observable. So what you can see is either this one or this one. So this means that you have this one-to-one correspondence of PBH mass or the induced quantum frequency. So you move around here, then this peak move around. And the amplitude has a completely one-to-one correspondence. There is no parameter, but there is some uncertainty due to our unable to calculate accurately. I will talk about that later, but that's not so important. Anyway, so this is the kind of the picture from the observational side. I already said that we do not see this power spectrum. So what we see is the observation from PBH side or the gravitational wave side. So if we put them together and collect this frequency with the primordial black hole mass, as I said, they are collected by this K star. If you calculate a little bit, then you will find that this is the correct relation between the frequency on the right and the primordial black hole mass on the left. And because of this, you can see that all of these windows, possible interesting windows where there are some implications of either or the dark matter or microlensing events, you see something here, or the LIGO events. Because you have some LIGO events, black holes spanning together, and that you cannot guarantee that all of them are from astrophysical origin. So you need 1 or 2 or some implications that you have this, or subsolar mass LIGO candidates, you have something here. So then you can transfer all of these implications to the peak on the induced gravitational wave signal. Like for instance, LIGO events corresponds to some frequency which is right below the pulsar timing array. So 10 to minus 10 to 10 to minus 9 hertz, which if you have a broad power spectrum, can even go beyond this and fit your recent PDA data. The microlensing events is in the intermediate range, a little bit higher than this positive timing array frequency. So 10 to the minus 7, 10 to the minus 6 hertz. And all the dark matter corresponds to the millihertz case. So this correspondence is very important if you want to seek for the corresponding data. And also there is a one-to-one correspondence of the amplitude, as I said. So all dark matter is already constrained by these lines. So this is a PBH to be all dark matter line. And reflect it a little bit because it depends on the shape of the power spectrum.
In the LIGO observation is order of hertz, right?
Yeah, 100 hertz.
Yeah, 100 hertz. But in the horizontal line, is it 10 to minus 9 or 10 to minus 10?
That's a different thing. So LIGO, the observation, the gravitational wave LIGO has already observed is the gravitational wave from the in-spiral for the black holes. Yeah, that is one thing. And this one is the so-called induced gravitational wave. It comes from the curvature perturbation at the horizon crossing to generate such solar mass black holes. And in that case, the frequency are much lower. It's like 10 to the minus 9 hertz, the locate scale. It corresponds to LIGO black holes, but the frequency is here. Yeah.
So typically, more massive than the smaller frequency.
Yeah.
Sorry, in the plot on the right, there is a dashed line, horizontal line constraint that PBH are less than dark matter. Right?
Yeah.
So what is the meaning of the observations above them?
Above this one. Yeah, that's true. If it goes above that, then it means that you have a more primordial black hole than the current dark matter if you use the Gaussian statistics. So this usually means that you may have some non-Gaussianity to suppress the PBH formation. I will come back to this later, but as you mentioned that you asked whether there is any parameter to determine this correspondence. If you assume Gaussianity, then no parameter already. But if you introduce non-Gaussianity, then you have F1L, GNL, whatever. This will comes into play. Yeah, that's the main topic of the talk. So this reviewing some previous work. My work is talking about this non-Gaussianity stuff. So this is the PBH constraints. I zoomed in a little bit. So for the primordial black holes, which are already have already evaporated by today, small primordial black holes, like the mass is smaller than 10 to minus 16 solar mass or 10 to 17 grams down to the Planck mass. You have also have constraints, but this is mainly from this thermal history, so different things. We are more interested in the primordial black holes which can exist for today than is this figure. So you have the constraints from 10 to minus 15 solar mass up to the almost the mass of the entire universe. So you have all of these different constraints. And use these constraints, you can reconstruct the power spectrum of the curvature perturbation like this. This is very easy to be done. And this is a kind of also analog. So dark matter community are familiar with this figure, which is a kind of a constraints for the WIMP particle. And you can refresh these experiments, different experiments in a few months. And this is approaching the so-called neutrino background, and it seems more and more difficult to probe such things. And this one is the constraint of the primordial black hole dark matter. And also you have many constraints, and now you still have this one window where the primordial black hole can be all the dark matter. So it seems that this one wins a little bit.
So 10 to the 15 in the left hand side, previous one, 10 to 15 times solar mass, is that window or ruled out? That's the white region, yes.
This one. This is not ruled out, but in that case, you may have a
Even
that's a galaxy size. So if it's very remote, then you may not see that. So observationally, it's a lot.
The set of the black mass of the black hole is the set of the galaxy.
even that's much heavier. There's a 10 to 15 solar mass.
26 to 28. Yeah, I think so.
Yeah, but the white region is the 10 to 15 of this one.
It's more heavier. I don't know.
Yeah. I think.
There's no observation on that.
Yeah, I think Bernard Carr had some paper on that, but I didn't read them carefully. But anyway, so this line is the constraint that there is at least one primordial black hole in our entire universe. So you can see that it reaches one means that the entire universe is one black hole. So if there is even any primordial black holes, then it should be above this. So let's focus on this part. So I will focus on this part of the figure and introduce a little bit more in details how these constraints are implied. So again, let me just say that this FPPH on the horizontal axis is the energy density of the primordial black hole today, normalized by the energy density of dark matter today, which is the mass of primordial black holes. So there are many interesting windows, as I show a little bit here. You may have this quantum gravity effects called the memory burden, proposed by the Giardali, and he said that if you have this, then the Hawking reverberation is greatly slowed down. Then you may not have such a strong constraint on the small side. I will not touch this. You have asteroid mass primordial black hole, which can be all dark matter. I will tell you the reason why. And the planet mass can locate here and serve as some microlensing events. So microlensing experiments are stopped here because they see something and they cannot identify the origin of that. So if they are primordial black hole, then they are, of course, 1% of dark matter. And the solar mass, this is already, we already see. We have hundreds of LIGO events, but yeah, even one of them are from primordial origin, then you can have 1,000th of dark matter. And even they can be the supermassive black holes and serve as seeds for the galaxies, or little red dots, or whatever. These are also very interesting topics, but may need some more information about the observation on high redshift. Anyway, I will focus on these three windows. First of all, so the primordial black hole as LIGO events has some implication that you may have a few of them coming from primordial origin. This is done by these groups of people. They said about 3% to 50% of the events might come from primordial black hole. And their reason is that if you put all of the families of these black holes together, and you find that they are not fitting the data quite well. If you add one extra PPH family, then this looks better. So in that sense, they say, okay, you can have this primordial black hole population in these LIGO events. And if that is true, then it can be at most 1,000th of dark matter around here. Of course, you can seek for the subsolar mass primordial black holes. And if you find even one event of that, that's the kind of smoking gun of a primordial black hole. And this has been done by the LIGO and many related papers. And like, for instance, this is so-called subsolar mass. 2020, March the 8th, they found some kind of candidates of which the mass, both of the masses are below the one solar mass, and SNR is as high as 8.9. Well, let's see what will happen.
So that observation is not from LIGO, but from what?
I think this is from LIGO. Yeah,
Oh, from LIGO.
yeah, in this paper. Yeah, LIGO group, they have a paper searching for these subsolar mass candidates. You can, take a look, and then you have also some other papers seeking for more. If you have a different template, and you can have a better rate for that.
You have other channels which can make the black holes appear as if they were lighter than a solar mass, like demagnification.
Yeah, that's also true. So yeah, this is optimistic, of course. So we also have some candidates of the so-called macro-lensing events. So the OGO found some 6 ultra-short time-scale lensing events in their survey, and this is this green one was their previous result, so it's affordable to this, and their new result is like this, already excluded this region, but this is criticized by Takehiro Takada, and they are writing a paper for that. But anyway, so it is true that we may have some planet mass candidates. And let's back to this most interesting window where the primordial black hole can be all dark matter. So why can this? The reason is these microlensing experiments cannot go down to this region, mainly because of this so-called finite size effect and the wave effect. Wave effect is quite simple. So in this region, the wave optics is not applicable anymore. So you have to go to the so-called sorry. So the other way around. Geometrical optics is not applicable anymore. You have to go to the wave optics. So this is give you some constraints. And also the finite size effect means that because the primordial black hole or the lensing object is so small that it cannot block the light goes directly from the star to the telescope. So this means that even if you cannot see any variation of the light luminosity, you cannot exclude the small, very small primordial black holes going around the IO site. So because of this reason, this is the so-called only window, and it cannot be observed even in the future by any optical observations. If you can find any X-ray or some other more fancy microlensing experiments, then yeah, it can be seen. But for optics, no. So then you can write a lot of papers saying, okay, we can have a peak here generating primordial black hole as all dark matter, and so on and so forth. I guess there are like at least 500 papers talking about this possibility. Anyway, so primordial black hole is an interesting link of a macro and microphysics. So this is the Ouroboros eating its tail, which means that I borrowed this from Florian Kuhnert. You can see that for all of the scales, it's possible that we have a primordial black hole of that mass. So, of course, supermassive one, this is what Professor Lee talked about. And we have a primordial black hole of the intermediate mass range, stellar, terrestrial, lunar, and evaporating, and so on and so forth. Very interesting. So now it goes to the main part of the Gaussianity. It seems like I already got too much time. Anyway, I'll try to be quick. So as I talked about, such kind of a cross-check looks okay, but there is one loophole that we may not have a Gaussianity in such kind of a calculation. The main reason is that, as I mentioned before, when you enhance the power spectrum, this enhancement usually brings non-Gaussianity if you try to construct the inflation models. That's quite normal. So in the case of there is non-Gaussianity, then the one-to-one correspondence of the abundance and amplitude will be broken. But interestingly, if you only consider simple non-Gaussianity of, for instance, this type, this quadratic non-Gaussianity, in this case, it doesn't matter. The result is quite robust. If you enhance the F and L, this means that the tail, this is a positive skewness for the positive F and L. This means that if you have a larger F and L, then you have a more primordial black hole. But if you fix the primordial black hole abundance as the order dark matter, for instance, this means that the variance of the curvature perturbation needed is going down from, for instance, 10 to minus 2 to 10 to minus 3 in the limiting case. This shrinks a little bit, diminishes a little bit, but it predicted the induced gravitational wave also going down a little bit. So from like, for instance, 10 to minus 9 to 2 orders of magnitude, because this is a square relation, right? And goes to 10 to minus 11, for instance. But this is the limit of that, is the lower bound, because this is already the so-called chi-squared statistics, where the f(n)(L) goes to infinity. So this means that the Lisa Taiji tension, this space-bar interferometers, can always probe the primordial black hole dark matter, even if there is a simple non-Gaussianity like this. You also have to say, okay, f(n)(L) is infinity, then how about the higher order terms? That's true. We have to specify a model in that case. Otherwise, you have infinity series of these parameters by the perturbative expansion. So that's the my recent work, which I will introduce soon. So let's go back to the calculation of primordial black hole for a while. I already talked about this PDF of the density fluctuation. So you have a critical value, then you cut it here, and this will be the primordial black hole. That's what we do. But if you want to do it more accurately, you will find at least 3 loopholes of this calculation. So one, the linear Poisson equation is wrong, because if you go to higher order, apparently this is not the case, this one. And the second one is that if you have enhanced the power spectrum, in many, many models, the curvature perturbation is not Gaussian anymore. Then you cannot have a simple relation of the PDF by a linear statistics. And finally, there are some recent discussions on how to choose the critical density. It depends on the profile, which in turn is determined by the shape of the multiples of the fluctuation, which I will not touch now. But anyway, so what is the real thing? This is only to show the result. So we have a nonlinear relation from the curvature perturbation to a new variable called compaction function. And the compaction function can be used to calculate the PDF of the curvature perturbation and so on. So then we calculate the abundance of the primordial black holes. This is a little bit complicated, but I will just show by this figure. This is the figure shows the delta, which is was the variable we used, the density contrast. It is also the linearized compaction function. Forgot about that. So if you take the Gaussian statistics, then you have this red curve. But the real statistics is the blue one, exact. So, and the PBH formation abundance is integral from in this gray strip. So you can see that it's kind of 10 orders of magnitude higher if you take the statistics corrected. So that's the thing we must take into account. And sometimes you need more accurate method, then you have to go to the peak theory, which I will not touch because of time limit. And just skip this part. Okay, now let's go to the one important part of the primordial non-Gaussianity and see how this primordial non-Gaussianity is necessary when calculating the PBH formation. The reason is that, okay, you have the so-called delta informism to calculate the primordial curvature perturbation from the inflaton perturbation of delta phi. So I will skip this. But anyway, so the curvature perturbation is depicted by the difference of Euclidean numbers of the expansion of 2 different remote parts, like this A and this B. So one is a fiducial one, and the other one is the one you are going to study. So because of the fluctuation of the inflaton, you have a kind of a quantum cloud, something here. So each point represents a separate Hubble horizon during inflation. So this has a statistics of delta phi, usually it's a Gaussian. But this Gaussianity doesn't mean that the curvature perturbation is Gaussian, because this relation, the difference of E40 number, can be highly nonlinear. And by this, you can calculate the PDF of the curvature perturbation. And this one is Gaussian, this one might be Gaussian, but this is a nonlinear relation usually, which I will show later. In the simplest case, this is a linear relation, this one, this Jacobian. This is guaranteed by the slow roll parameters. So if you go like a slow roll, then you have a kind of power spectrum of near scale invariant manner, and R and delta phi is proportional to each other. But things will change if you have an enhancement like this. This is what we call an ultra slow roll. Ultra slow roll means that it's extremely flat, and then you have a deceleration of the slow roll velocity, which means that the power spectrum enhances because you have phi dot in the denominator, right? The key point is that whether you still have this linear relation of this, and the answer is no. If you put it in the power spectrum, you can only see something like this, which is far, far different from the real power spectrum of the curvature perturbation. And the reason is mainly because during this period, the so-called decay mode becomes more important, and which is usually neglected in the slow roll calculation. So once you take that into account, then you can have the real relation, and the non-Gaussianity is huge. It's of order 1. So in this USR case, the so-called 5/2. And this is not the end of the story, but I will skip the calculation, but just to let you know that the result is, fortunately, we have this compacted result of fully nonlinear relation of the curvature perturbation and the inflaton perturbation. This is written in the velocity perturbation. The pi is the phi dot. So in this case, if you expand, you have f(n)L 5/2, g(n)L is something, and so on. So you can expand forever. But because this is order 1, if you cut it at anywhere, this is not a good way to do. So you have to take into account the nonlinear relation into account. But fortunately, this can be done, at least for the calculating of primordial black hole abundance, because we only need the Jacobian of the relation of curly R and delta phi. Like the one we have here. This is the picture I already shown. This is done by the Riotto group. And if you use this relation, and then you...
Here, so for the ultra slow roll, so how many parameters are there for the ultra slow?
For the ultra slow roll, there is only one parameter, is the initial velocity, which is depicted by this delta pi star.
So that's the pi is the velocity.
Yeah.
I know.
Pi dot. Pi dot is the velocity at the end of... pi star. Pi star is the velocity at the end of the USR stage, which is determined by the initial condition, of course. You set pi 0 here, for instance, and you have equation of motion, then you have the pi star. That's the only parameter. So you have a larger pi or a smaller pi, then you can have a different pi star here, which gives a different...
Pi star is determined by the quantum fluctuation.
Yeah, this one is kind of fixed, because this is determined by the quantum fluctuation. Yeah, so it's order Hubble or something. Yeah, that's kind of fixed by the background.
What about the shape of the potential? The potential V phi.
The shape of the potential is like, it doesn't rely on that much, because we already know that the main part is this flat potential. But this junction to the later stage is really important. I will come back to this later. Yeah, because this will determine whether the curvature perturbation generated here dominates the total curvature perturbation.
So this is a discontinuous.
Yeah.
The relative is discontinuous.
Yeah. Discontinuous means that this one can dominate, and the final curvature perturbation is this. If this it's like this, then you still generate a lot of curvature perturbation in the later stage, And this might not be the final one. So you should add the contribution from the later stage, and the non-Gaussianity might also be changed.
also G and L. G and
Yeah, GNL, what is the definition? FNL.
You just explained. So it's like so your curvature provision is curvature provision Gaussian part plus FNL curvature provision squared, GNL curvature provision cube, and HNL fourth, so on and so forth.
higher.
You can do it in this series. You can.
One question is to create the full equation of the information, the E4, still the E4 numbers if you want.
The background E40 number of this point is in the middle. It's after the CMB scale, but before the end of inflation. So it can be set like 40, 50 or something. 40, let's say 30, 40. It's determined by the K star. So where you want the power spectrum to be enhanced. So like for instance, if you want to enhance it to be all dark matter, then I forgot the number, but M is like 10 to the minus 15 solar mass, that kind of window. Then K star is something. I think the E40 number is like 40. Yeah, counted backwards from the end of inflation. So like for instance, this is a E40 number 40. End of inflation is here. E40 number is 0. This is 60, what you need for CMP. Because this is a slower potential, then this is okay. And on large scale, world observations fit quite well. And here you have a very tiny flat potential to enhance the power spectrum on small scales, then you have a Primordial Black Hole and this one. Okay. So what we contributed is kind of we extend this previous study because this is quite a simple thing. We want to make it general, so we use this piecewise quadratic potential. Because the key point is that the equation of motion can be solved in this quadratic potential. Piecewise means that we need this discontinuity to make the inflaton out of the attractor solution. And we already know that this so-called out of attractor is the necessary condition to enhance the power spectrum because the decaying mode will only be effective in the moment where the inflaton deviates from the attractor solutions around this border or junction. I will not go into details because of the time limit. But anyway, so the result is that we found the kind of fully nonlinear relation of the curvature provision R and the initial condition delta phi delta pi around here. And it's kind of a later evolution of delta pi star at the border.
All the piece of the potential and the
Quadratic.
quadratic order, not the quantic order. So there is a special reason.
Yeah, because in the quadratic order, the equation of motion can be solved analytically.
When you construct this piecewise potential, you impose that the derivative is continuous, the second derivative is continuous, or
we assume the power, the potential is continuous, but the slope may not be continuous. And actually that is necessary because actually this is an extension of this. So the USR model is like this. So you have a slow roll potential and you have some constant slow roll velocity. But here you have a flat potential. So it decelerates. This deceleration is the deviation of the attractor. So this is necessary to enhance the power spectrum. And we kind of extend this to quadratic pieces. So it's the same. So you have a kind of a constant you have an attractor solution on the quadratic piece, which is different from the constant attractor solution on this quadratic piece. So it either accelerate or decelerate. And during this stage, this is similar to USR. Actually, it's called the constant rule. You can enhance or suppress the power spectrum depending on the whether you are accelerating or decelerating.
Sorry, probably it takes too long, but when you talk about the attractor solution, usually you have in mind some autonomous equations and some you write the evolution of phi and phi dot.
That's true. That's what we did in cosmology, right?
Yeah, exactly.
So in cosmology, we always have phi double dot plus 3h phi dot plus v prime phi equal to 0. This is the background solution of the inflaton field phi. And usually, you have two solutions. Let me just do it here. This is the equation of motion for phi, written in the folding number n, but basically it's just this one. So you assume the quadratic piece, then this eta v is a constant. It's m squared over 3h squared. It's different in here in this green part and the red part, but on this part, it's a constant. On this part is another constant. So you can solve this equation on either here or either here, but the only thing you have to do is to make the correct junction. That is what we already familiar with in cosmology, right?
The attractor is due to the sign of lambda plus and lambda minus.
Yes, that's true. The attractor means that if you make the folding number here, the folding number is counted backwards from here to here. So if folding number goes to 0, which one is larger? So if folding number goes to 0, then you can see that the lambda minus lambda plus, of course, the lambda minus will be dominant, and that is the attractor solution. That's what we call. It's a late behavior. Late behavior means that you decay slower along this. And if you put this to all of the models, you see you can immediately see that. For instance, in this USR case, the solution is phi equal to C1 plus C2 exponential 3n. N is counted backward, n equal to 0 to n to something. This one is the attractor solution, because if n goes to 0, then this is the only solution. And this is the non-attractor. We need this non-attractor to get rid of this flat potential. So this is crucial, necessary, crucial to enhance the power spectrum and also to end the inflation. It's similar to the case here. If you want to shoot from this side to the other side of the bump, then you need the non-attractor solution, because attractor solution is to stay here and roll down. And not only non-attractor can go beyond this part. So, and that is the one which can enhance the power spectrum. Otherwise, you just go following this slow and nothing interesting. Yeah, maybe I shouldn't skip this USR part, because this can be easily seen from this ultra slow inflation solution. In this case, you do not have a V prime, so the solution is like this. So just a constant plus exponential 3n, and you can solve this exponential, the folding number from this one and its velocity. Actually, it's like this. And then you can calculate the curvature provision curly r, which is delta n, and it's the difference of this anterior and n, which give you this one. This one is negligible, then you have this. So this non-attractor solution is necessary. Otherwise, you cannot end the inflation. Anyway, so if you correctly take that into account, you can have this kind of solution. And for each piece, like for instance, this piece, you have two terms. For this piece, you have two terms, and so on and so forth. You have many, many different pieces. If the potential becomes more complicated, then you have more terms, but in principle, it can be done analytically. That's the point. So after we reached this formula, we checked all of these similar relations, like this slow roll solution. This is quite easy. Slow roll solution of this one is just the Taylor expansion of this. Take F and L to be small, and you have this. Quite simple. But recently, I found that if you want to recover the Maldaceno's consistent relation, this is not enough. You have to take into account the non-Gaussianity of delta phi itself. So this means that this relation only gives you the non-Gaussianity on the boundary, but not in the bulk. Yeah, I'm working recently with Takahiro and the collaborators on how to deal with such kind of things. This is related to the recent hot topic of the so-called loop corrections in the ultra slow roll. So I will come back to that later. But anyway, so this one is the constant row. We only have this one logarithmic term. This constant row is the model that you only have this one bulk exponential, nothing else. So then you have only one of this term. Sorry. And this is the ultra slow roll I already introduced. We also have this Curriton scenario, which is actually two field theory, but it's effectively single field. And we can also extend that to some more complicated form that it's a logarithmic of a function of some Gaussian distribution. So anyway, by this, we can calculate by the probability conservation to calculate the PDF of curvature provision. Because we know that the delta phi is Gaussian, at least we assume that the non-Gaussianity of delta phi is very small, suppressed by slow roll parameter. As I commented before, the non-Gaussianity of delta phi is suppressed by epsilon, and that is necessary if you want to recover Maldaceno's consistent relation. But here we do not need it. Then I assume that it's purely Gaussian. And this P of delta phi is a Gaussian distribution. Now you can calculate by this Jacobian to have this probability distribution function, which seems a little bit complicated, but you can see that this is from the Jacobian, and this one is just the previous Gaussian part from delta phi. You just change the delta phi, so delta phi from here, then you put it. You can see very interestingly, it depends, the shape, the tail shape of this PDF depend on the signature of lambda minus. If lambda minus is negative, then you have an exponential negative something r. This is so-called exponential tail. This will enhance greatly the tail of the PDF and enhance the abundance of primordial black holes. On the other hand, if lambda minus is positive, this is an enhancement, but you have a further expression in here, exponential minus something times exponential something. This is a double exponential suppression, which is similar to the Gumbel distribution. So in this case, the primordial black hole formation are highly suppressed. I have to emphasize that such a calculation must be done in this way, fully nonlinearly. You cannot do it by the perturbative series. If you do that, then you have some result, but that is apparently wrong. And this is a schematic figure and maybe difficult to read. In the Gaussian case, you have some primordial black holes, and in the expansion tail you have more, and in the Gumbel tail you have a very big. That's some similar kind of a schematic figure with the Williams figure, just to show the effect. Anyway, so I think I will skip the examples of constant row, Curriton, USR. Yeah, this is a discussion about the junction point. So whether we have a USR with a continuous end or a sharp end will give you different result. The main reason is that the contribution from this side will be larger than this or not. This is a little bit complicated, so more detailed, so I will skip. I will go directly to the observation, predictions on the millihertz and the nanohertz gravitational waves. Hope I can finish in like 10 minutes. And I will not exceed too much. Okay, based on the discussion before, we already know that we have this one-to-one correspondence of primordial black hole as well dark matter that you can calculate the induced gravitational wave in like this. And also in this quadratic expansion or in this logarithmic relation, it doesn't matter you have how the non-Gaussianity, what non-Gaussianity you have. For instance, here we have this quadratic expansion and also the USR. If you have higher and higher F and L, as I have shown, this induced quantum wave will need it to generate the primordial black hole as dark matter will be smaller and smaller. There is a chi-squared limit where the second term becomes very, very large. Then you have this green curve, which is still above the Lisa-Taiji tension sensitivity curve. So this is some take-home message. When the PDHs are all dark matter, you must see the signal of the induced gravity wave in the space-bound interferometer because it's still well above this. And this moves around if you have different methods, but it doesn't matter. This is shown in a recent paper, which I forgot to put. But anyway, this is the conclusion. The signal is robust against the non-Gaussianity. And recently, we also work on some more fancy part of this logarithmic case. I will talk about that later together with this nanohertz gravitational wave. So this is maybe some people are more interested in. This is the second application. We know that actually the implication was in 2020, but in 2023, all of these 4 pulsar timing array experiments reported some strong evidence of the detection for a gravitational wave background around the 10 to the minus 8 Hertz, as is shown in here. So I only show the Helly-Stans curve of nanograph and the so-called Chinese pulsar timing array, and also there are EPTA and the PPTA have similar figures. This is borrowed from the paper of nanograph analyzing the new physics models. We are kind of a theoretical physicist. We are more interested in new physics models. Although it can also be fitted by the so-called astrophysical model, that's another story. So in this new physics model paper, they show the comparison of the Bayesian factor for these different models. And it's seen that all of this, almost all of the cosmic stream models are quite bad. The favored models are the induced gravitational wave models. The Bayesian factor are like 60 times the base model. This is the astrophysical. This baseline is the astrophysical interpretation. So as you can see from here, because the cosmic strings always require that you have a plateau after this energy scale. But if you look at these violins for the pulsar timing array, it didn't see any tendency that it goes down. So if everything goes up, then the induced wave actually looks much better than all of these other kind of interpretations.
So
But
the primordial black hole, how do they induce gravitational wave?
That was as I said, that is because the coverage observation, which collapsed into primordial black hole, has the gradient term, and that can generate this so-called induced gravitational wave. I introduced that a long time ago, but it's the same thing. So if you use that induced gravitational wave to interpret this pulsar timing array data, the Bayesian factor is temporarily the best, as is shown here.
But even if the density flotation is not that big enough to collapse, so that kind of induced gravitational wave should be produced.
Yeah, that's true. It's still there. If there is not enough primordial black hole, you may also have the detectable induced gravitational wave. Yes, actually, that is exactly the implication of this part. So you can see that there is still a huge space around here. So if you see induced gravitational wave around here, then it's not enough to generate the primordial black hole as well dark matter. But still, you can see the signal. That's true. Yeah, but the conclusion is made reversely. So if primordial black hole are all dark matter, then these signals are strong enough to be detected in the future. Anyway, so yeah, in this case, induced gravity we can interpret is quite well, but there's a yeah, you can see it from this figure. So from this signal of nanograph, you can write down this wavelength of the omega GW. You can see that if it's like 10 to the minus 9, then power spectrum is 10 to the minus 2. As I already said, okay, primordial black holes are just here, can be all the microlensing events. It looks quite good, but this is not exactly the case because this is not the best fit. If you raise it to the best fit, that is around 10 to the minus 7 or something. This is too large. You reconstruct the power spectrum to be 10 to the minus 1, then the primordial black holes are more than dark matter. So this is a problem, actually. If you look at the nanograph paper, you will see it clearly. Let's forget about this log normal power spectrum for a moment. Just focus on the delta function peak, so-called the monochromatic mass function case. In this case, nanograph result is here in this colored region for the amplitude and this peak frequency F star. And this colored region is almost excluded by the FPP equal to 1 line. So this above this line is too much primordial black holes. So you can see that 1 sigma level is already excluded. Of course, this is possible if you stay here, but you can see that the sweetest spot is already gone because it predicts too much. So what can we do? We have 3 kind of philosophies. So one is that, okay, you have more primordial black holes. Then we know that there is some uncertainty in the calculation of primordial black hole abundance. Then we just use some conservative way to calculate the primordial black hole abundance. Of course, this will suppress the abundance and everything is fine. We don't see any problem. That is done by many groups of people. But I think this is not a good way to see things because you choose a way of calculating by your heart or your own philosophy, not by observations. So not the other way around. And the other way is to suppress the abundance by increasing threshold. This is usually done by changing the equational state. So in the radiation-dominated universe, threshold that, but if you increase the equation of state parameter W, then you can
when you increase the equation of state W
around the moment where this perturbation re-enter the horizon.
So you assume that instead of radiation dominance, you have something else.
Yeah, I have something else. Something W is larger than 1/3. Actually, you can see that will increase the critical of the PBH formation and suppress the primordial black hole. And this is done by a recent paper with William and my students. And also, you can suppress the PBH abundance by negative non-Gaussianity. As I said, if you have positive non-Gaussianity, positive means that you have positive skewness. If you have negative skewness, then you have less primordial black hole. And this can also be done. But there is some subtlety, which I will talk about it now. So what will happen? In this case, as I said, best fit will give you too much primordial black hole. And if you have a negative non-Gaussianity, it can suppress primordial black hole, and everything is fine. But the problem is, it's too much suppressed for the FNL. So FNL is, according to the analysis by many groups of people, FNL should be suppressed to around the -10 to do the job. But we know that if FNL is like -10, then you cannot trust the result anymore. If it's not so small, like for instance, in the curve in the model, FNL is -1, you can see that the result is okay, but it helped only a little bit. So raise the result from the black line to the blue line. So it's still far away from the center of the likelihood. So if you want to make FNL even smaller, then you meet a serious problem of the non-perturbative calculation of scalar-induced gravitational waves. So this is a kind of done by in our paper recently, because the FNL is too negative, then you have a larger and larger amplitude, then the higher order terms of the induced quantity become larger and larger, and finally you cannot calculate by the expansion series. And our final result is that if you look at the Bayesian analysis in this figure, this is the crucial one. So this blue region is the nanograph results, implication on the amplitude of the coefficient perturbation, and this gamma factor. Gamma is the related to FNL. You can refer that to just to FNL. So if gamma is negative, it seems that it's okay. This A is going down and this PBH is coming up. If they meet, then it's perfect. You have primordial black hole to be all dark matter, at the same time explain the data. But actually, this region is non-perturbative, so it's not trustable. So in this case, this is an open question, in the sense that before you find a way to calculate the induced gravitational wave non-perturbatively in this region, you cannot see anything about.
Can you remind again what is gamma definition?
Gamma is the, let me just write. So we parameterize the curvature perturbation as 1 over gamma logarithm 1 minus gamma RG. So gamma is a kind of FNL. There is a ratio between them. Gamma is like 3 or 2 or 3 FNL or something.
I see. So it's connected to FNL.
Yeah. So if gamma is too small, smaller than -4 or something, the higher order terms of the induced gravity will become larger and larger, then you cannot calculate by perturbative series. Drawing Feynman diagrams, whatever, this is not trustable anymore. So you should use lattice simulation or some other more reliable things. So before doing so, we cannot say anything about interpreting the nanohertz gravitational wave by the induced gravitational wave. And that's the third part of the conclusion. Previous conclusions are primordial non-Gaussianity must be taken into account when calculating primordial black hole abundance. And we found that fixing the PBH abundance, the prediction of induced gravitational wave at millihertz is robust, which is an important scientific goal for the spaceborne interferometer. And finally, this must also be taken into account for calculating the nanohertz gravitational wave. And that is an open question. Thank you very much.
IC and the TNT, they are covering some similar frequencies.
Oh, yeah, sure. I think I have a figure in the first part. Yeah. In this figure, you can see it clearly. This solid line is Lisa. This kind of a dashed line is Taiji. Dotted line is Tianqin. So Tianqin is a slightly, the arm of Tianqin is slightly shorter because Tianqin is on the Earth orbit. The other one are in the solar orbit. Yeah. So you can see that this slightly changes a little bit. And also because the arm is shorter than the sensitivity is slightly weaker, so it moves around to the upright. Yeah, that's the main difference. The Lisa and Taiji, I cannot see any difference from the configuration. This difference of the scaling is just due to the there are different configurations. It doesn't matter.
Okay, so I have actually couple of questions. They are all related to this statement in red, which seems quite a strong statement.
Yeah,
In
yeah.
a sense. So the first question is related to the adjective relatively robust.
Mhm.
I mean, it's a very strong statement. If you have a minimal signal below which you can rule out the model, basically.
Yeah, yeah.
And this including also FNL infinity. I mean,
That's
this is okay. So I would like to. So is there any loophole? For instance, if FNL is very large, then you cannot trust the calculation.
you can actually. That's
some loopholes. The second is related to this because this statement seems quite robust, it's strong. But later, when you discussed the gravitational wave observation,
nanometer.
the nanometer, then nanograph.
Yeah, yeah.
You said, okay, I have an overproduction of black holes. And then you listed a long list of possibilities to reduce this. But in light of this statement, your opinion is that they are not basically the tension remains. Yeah. So this is related. So the point that the tension between ganograph and the abundance of black holes.
Yes, is related. Yeah, yeah, you're right. So yeah, this here I make this claim quite strong because this is my work. So,
okay.
Of course, there are
some loopholes.
Yeah. Of course, there are some something. If you want to object this, then you can do something. For instance, if you construct a model with a 0 FNL but very negative GNL and so on and so forth, you can adjust these different coefficients and try to suppress more of the signal. That is possible. But the problem is that if you do that, you cannot construct a model. So we know that if you want to do this predictive research, you have to specify a model. Otherwise, you
you mean, for instance, an inflationary potential.
Yeah. If you do that, if you give a model, then this is always true. This is always true. This is one thing. Yeah. From the model building point of view. And the other thing is that what you mentioned, this philosophy I borrowed in the later part. How about the change in the equation of state? That is something that changing the equation of state can also suppress or enhance the PBH formation and change the robustness of this prediction. That I agree.
So we have no idea what is the equation of state. Before we get.
That's true. So when I state this, I have some precisions that you have a normal model, a model building of the single field inflation, enhanced power spectrum in the ultra slow or whatever, and in a radiation dominated universe. That's true. Yeah, I didn't put that, but I thought that was something that we have. We all agree that must be some preconditions for what I have.
In vanilla cosmology, without any change, this statement is relatively strong.
Sure. And because this is a kind of a positive consequence, that we can look it in the other way only when we do not see such a signal. So this is something that you say, okay, so we build this space-bound interferometer, put money in that, and this is a very important scientific goal to prove. But if you really do that and you cannot see it, then you can see something like, okay, now we construct some other ways that the deviation of the standard vanilla model, which explain the absence of such signals. That's true.
Yeah, but the point is that, for instance, if you don't observe anything and you believe in the cosmological model, basically you rule out the possibility that black holes.
Then basically we rule out the primordial black hole as well the dark matter. That's the key point. Yeah.
You can still
try to construct some model which can suppress this even lower, but that's not promising anymore, I guess. Yeah, because this robustness also. Yeah, I cannot see its kind of mathematical proof, but physically for a physical background which most of the cosmologists accept, this is this statement is strong enough, and I think this set a very good scientific goal for the future probe for the space-faring interferometers, and we also write it in the white book in this governmental report to propose the Tianqin and the Taiji. Yeah, so we should be positive in that sense. That's the reason why. Yeah, I admit that it's a little bit too strong, but that's what we should do before we do any experiment.
One question. There's also the lunar gravitational wave antenna, which should also go roughly in the 80 Hertz band. Do you have any hope that one can also detect something that if it then works?
Yeah. You are talking about You are talking about the lunar-based interferometers. Yeah, Shang also talked to me something about that. It may appear in let me go to this one. So it may appear somewhere here, right? Maybe 10 to minus 9. Yeah, this part. Yeah. That's true. That's very important. But the key point is that in this frequency band, usually you do not see any primordial black hole because this corresponds to the mass in this window, which is already excluded by the extra galactic gamma rays from the Hawking radiation, unless, as I said, you go to some more exotic models like this so-called memory burden effect. So if you want to have some primordial black holes of this mass, then you need some fancy quantum gravity stuff. Maybe that's even more interesting. Yeah, because you not only verify the existence of primordial black hole, but also some quantum gravity. Yeah.
Measurement.
Yeah.
Have one theory.
Sure.